The James Webb Space Telescope has once again reshaped our understanding of the universe. When its instruments detected the interstellar object designated 3.I/ATLAS, astronomers initially assumed it would resemble other known wanderers like Oumuamua and 2I/Borisov, small icy or rocky bodies ejected from their home systems, drifting between the stars. But as Webb's infrared eye began to capture detailed spectra and images, the data revealed something profoundly unexpected. 3I/ATLAS was far larger than anyone had anticipated. What was thought to be a modest interstellar traveler turned out to be an object of staggering scale, so immense that it challenged our assumptions about how such bodies could even exist, let alone survive the violent ejection from a planetary system into the interstellar void. The first observations came when 3.I Atlas entered a region of the solar system where it could be clearly observed by both ground-based telescopes and Webb's near-infrared camera. Initially, optical tracking data suggested a dim and slow-moving body, likely a few kilometers across. But once Webb began its deep infrared imaging campaign, the faint speck became a rich tapestry of reflected sunlight and thermal emission. The intensity and wavelength distribution of that emission pointed to a surface area that simply didn't fit the previous estimates. By comparing the infrared brightness to the predicted reflectivity, astronomers calculated that 3.I/ATLAS could be hundreds of kilometers wide, orders of magnitude larger than either of the previously known interstellar visitors. That revelation sent shockwaves through the astrophysical community. Objects of that size are not easily ejected from planetary systems. Smaller comets and asteroids can be tossed out by gravitational interactions with gas giants, or by the chaotic dynamics of a young star system. But something of this magnitude implied an origin in a much more extreme event. Some scientists proposed that 3I/ATLAS might be the fragmented remnant of a dwarf planet that was torn apart by gravitational forces near its parent star before being flung into interstellar space. Others speculated that it could be a piece of a disrupted moon, or even a planetesimal core, the dense building block of planets that was expelled before it could accrete into a world of its own. As the Webb telescope collected more data, it became clear that 3.I/ATLAS was not simply large, it was unusually reflective and compositionally complex. Spectroscopy revealed a mix of ices, silicates, and metallic compounds that hinted at a layered history. There were traces of organic molecules embedded within its frozen crust, much like those found in comets from our own solar system. But the ratios were different. Methane, carbon dioxide, and more exotic hydrocarbons appeared in unexpected proportions, suggesting formation in an environment with higher radiation levels or different chemical abundances than those near the sun. Webb's mid-infrared instrument detected subtle absorption bands that corresponded to ammonia hydrates and carbon-rich compounds, pointing to a world that had once experienced thermal processing, possibly internal heating due to radioactive decay or tidal stresses. This mixture of characteristics suggested that 3I/ATLAS might not be a simple comet or asteroid at all, but a fragment of a differentiated body, a once geologically active world that had been torn apart. The discovery added a new layer to our understanding of how complex the building blocks of planets can be, even beyond our solar system. It also reinforced the idea that interstellar space might be littered with relics of failed or destroyed worlds, carrying with them chemical records of alien systems. The sheer size of 3I/ATLAS posed profound implications for planetary formation theories. To create a body of such scale and then eject it required energies and interactions far beyond what had previously been modeled for planetary system evolution. Traditional models suggested that large objects remain bound to their stars, while smaller ones could be easily scattered into interstellar space. But if something as vast as 3.I/Atlas could be thrown out, it implied that either catastrophic stellar events, like close encounters between stars, or the violent evolution of a massive companion played a role, or that there are mechanisms still unknown that can expel giant debris. Researchers began to re-examine data from young stellar clusters, where stars form in dense groups and gravitational interactions are common. In such environments, Close flybys between systems can yank entire planets or planetesimals out of orbit, sending them on long interstellar journeys. 3IATLAS might have originated in one of these stellar nurseries. Its enormous size and complex structure a frozen memory of chaotic birth conditions. If that were true, it would provide the first tangible evidence that large planetary fragments wander freely between the stars, possibly numbering in the billions. Webb's sensitivity allowed scientists to analyze how sunlight and the telescope's own infrared beam scattered off the surface. They found evidence of a tenuous coma, a faint halo of gas surrounding the object, indicating that 3I/ATLAS was slowly venting volatile compounds as it warmed under the distant sunlight. This coma was unusual because it was both extended and patchy, suggesting localized jets or vents rather than a uniform release. That pattern might reflect fractures in the crust, or differences in composition across its surface, perhaps remnants of the cataclysm that ejected it. The plumes also helped astronomers refine its rotation rate, revealing that 3.I/ATLAS turned sluggishly, completing a full rotation every several days. A slow rotation combined with such immense mass meant the object had significant structural integrity, perhaps held together by internal gravity rather than just frozen cohesion. That, in turn, suggested that 3I/ATLAS wasn't a loose rubble pile, like many small asteroids, but a cohesive, monolithic fragment. Such stability would have allowed it to survive for millions, maybe even billions of years, traveling through interstellar space without disintegrating. The implications for interstellar material exchange are enormous. If massive fragments like 3.I/ATLAS are common, then the universe is constantly trading planetary debris between star systems. Each piece could potentially seed young systems with complex materials, contributing to chemical diversity and even to the precursors of life. When these giant objects pass through planetary systems, they might deliver exotic compounds or introduce entirely new isotopic ratios into protoplanetary disks, influencing the development of planets and atmospheres. Astronomers studying 3.I/ATLAS used Webb's data to model its internal composition. The density, inferred from its size and the effects of sunlight-induced acceleration, suggested a mixed structure, dense rocky core overlaid by thick layers of ice and dust. That configuration echoed the structure of icy moons like Europa or Enceladus, leading to tantalizing speculation that 3I/ATLAS might once have been part of a system with liquid water below its crust. If that were the case, it could mean that interstellar space harbors fragments of worlds that once had subsurface oceans, potentially even environments suitable for prebiotic chemistry. Such speculation naturally captured public imagination. For the scientific community, though, the excitement was tempered by the rigorous task of verifying every piece of data. The Webb telescope's instruments are extraordinarily sensitive, capable of distinguishing molecular fingerprints across light years. But interpreting those signals requires caution. Teams across the world collaborated to compare Webb's observations with models of thermal emission and reflected light from icy bodies. Every analysis pointed to the same conclusion. 3I/ATLAS was far beyond the scale of previously known interstellar visitors.